figuring out what students really understand in science is, well, it's a major challenge in education right now.
Mm-hmm.
And AI is moving so fast. But using it for something like grading student explanations,
Mm-hmm.
especially not in English, that brings up some really tricky questions.
Absolutely. It's way beyond just marking right or wrong. We're trying to get at the students thinking how they connect evidence, ideas, explain things.
Right.
And then you add language differences, different cultural ways of explaining science. Yeah, it gets complicated fast.
Okay, so let's dig into this. For this deep dive, we've got two really interesting research papers that look at this from different angles.
We do.
We're going to explore how AI, specifically ChatGPT, is being used or tested for scoring science explanations written in Chinese.
Mm-hmm.
And then we'll also look at something pretty fundamental,
Yeah.
how students use analogies in science. Because that's key to understanding, right?
Exactly. So first up, we've got a study. It was just accepted in the Journal of Science Education and Technology. It's called Fine-Tuning ChatGPT for Automatic Scoring of Written Scientific Explanations in Chinese. Ji Yang and the team looked at the potential, but also, the hitches when using AI like ChatGPT for evaluating these detailed explanations from students writing in Chinese.
Interesting. And the second piece.
Then, to really get at what understanding means, especially for concepts that are maybe hard to put into words, we're looking at parts of a 2024 article from Science Education.
Right.
This one's by Jingwen Lin and Suyi Chao. And their work is about developing a tool, basically, to measure how well students can use analogical models. They use electricity as their example.
Okay, two meaty studies.
Yeah. So if you're listening and you're an educator, maybe looking for better assessment tools, or you're just fascinated by AI's limits and abilities, or, how language and learning interact, I think these deep dives offer some valuable stuff, maybe some surprises too.
All right, let's jump in. Why is scoring these scientific explanations so tough in the first place? Seems like it should be simple, but it's not.
You're right, it's not simple at all. A good explanation isn't just spitting back facts. It's about building a case, right? Using evidence, linking it to scientific principles.
Making an argument.
Exactly. And evaluating that kind of reasoning, well, it takes time. It takes expertise. Human graders really have to dissect the student's thinking.
And this skill, constructing explanations, it's not just a nice-to-haves, is it? It's actually a big deal in curricula worldwide.
Oh, absolutely. U.S., Canada, Australia, China, they all emphasize it. It's seen as crucial for scientific literacy.
So it helps students understand concepts better.
Yeah, and it gets them doing real science, like making sense of data, forming ideas. So finding better ways to assess it, that could be huge for science teaching.
Which leads us right to AI, automating this scoring process. That sounds pretty appealing.
It really does. The benefits could be significant. Less grading time for teachers, maybe?
Yeah, freeing them up.
And for students, maybe faster feedback, more personalized help. That could really tailor instruction.
And ChatGPT's been talked about a lot in this space. It seems pretty capable with text, especially English text.
Right, it's shown promise. But, like you said, mostly in English. And that's why this first study, the fine-tuning ChatGPT one, is so relevant. It asks, can this work for Chinese? Which is linguistically quite different.
Okay, let's get into those differences, because it's not just about swapping languages, is it? How might Chinese being different affect an AI like ChatGPT?
Exactly. Chinese is logographic, not alphabetic like English. That's a fundamental difference. The study points out things like Chinese writing can sometimes feel more holistic, maybe less linear than English analytical style. And reasoning can be more implicit. It might rely more on careful word choice than, say, strict sentence structure.
So where English might have a clear subject-verb-object thing that an AI can latch onto, Chinese might be more flexible, maybe expressing connections less directly.
That's a really good way to put it. And the researchers also mentioned that sometimes being implicit in Chinese writing is actually seen as, well, more sophisticated, whereas in English science writing, we usually value being very explicit.
Right.
So these differences in how you build and express scientific arguments could really challenge an AI trained mostly on English data.
Makes sense. Okay, so tell us about the study itself. What did Yang and the team actually do?
Well, they gathered a pretty big data set, 7,626 scientific explanations, written in Chinese.
Wow.
By middle schoolers, responding to 7 different science tasks. Then they used this specific data to fine-tune ChatGPT, basically teaching the general AI about the specific ways students write science in Chinese.
That's a solid amount of data.
Yeah.
So after tuning it, what were they measuring? What was the focus?
The main thing was scoring accuracy. Could the fine-tuned AI score these explanations accurately across different categories?
Okay.
But they also looked deeper. Like, did the complexity of the student's reasoning affect how accurately ChatGPT scored it?
Ah, interesting.
And then they did a qualitative dive, trying to pinpoint specific language features, words, sentences that seemed to trip up the AI or, conversely, help it score correctly.
So the big question, how accurate was it overall? Did fine-tuning work for Chinese?
The headline finding is pretty positive, actually. They got accuracy above 75% across the scoring categories, so definitely promising.
95%, okay.
But it wasn't uniform. Accuracy varied quite a bit depending on specific science task and also which part of the explanation they were scoring, like the overall score versus just the use of data or the reasoning part. Some items 6 and 7 they mentioned, had accuracy over 90%.
Okay, so decent, but variable. Now, you said they looked at reasoning complexity. How do they define that? What were the levels?
They borrowed from earlier work and set up 3 levels. Low complexity was like generalizing, summarizing, simple cause effect you can see.
Right.
Medium involved a few more variables, things maybe you can't directly see, trying to explain why, but maybe not using formal science ideas fully. And high complexity. That meant dealing with abstract stuff, unseen mechanisms, maybe forming hypotheses, thinking proportionally, more sophisticated reasoning.
Got it. And how did the AI's scoring accuracy connect to these levels? This sounds like where it gets really nuanced.
It really does. They did something clever. They split the students into 2 groups based on their actual score, a lower level group who got a 0 and a higher level group who got a 1. Then they looked for correlations between reasoning complexity and scoring accuracy within those groups.
What did they find for the students who got the answers wrong, the lower level group?
For that group, the correlation was mostly negative.
Negative, meaning?
Meaning, on average, the more complex their reasoning looked, even though it was scientifically wrong, the lower the score ChatGPT gave it. The average correlation was around meta 0.31.
Huh. So if a student was basically wrong, but used fancy-sounding complex language to explain it, ChatGPT marked them down more.
That seems to be the trend, yeah. It suggests the AI might sometimes be almost penalized complexity when the underlying science was flawed. It's like it got confused by elaborate incorrectness.
Wow, okay. That's a potential issue. What about the higher level group, the ones who got it right?
There, the picture was a bit different. They found a mostly positive correlation, but it was weaker and fewer results were statistically significant.
So positive link, but not as strong.
Right. The average of the significant correlations was about 0.19. It suggests that for students who are correct, demonstrating more complex reasoning tended to get slightly higher scores from ChatGPT, but it wasn't as strong a relationship as the negative one for the lower group.
Interesting. So complexity helped a bit if you were right, but hurt more if you were wrong and complex.
That's one way to interpret it. And they also noted this tendency for the model to sometimes, let's say, overrate complexity in the low-level responses and underrate simpler reasoning in the high-level ones.
So the way the idea was phrased seemed to be tripping up the AI sometimes, regardless of whether the core science was right or wrong.
Exactly. It wasn't just about the science concept. The linguistic expression mattered, which leads perfectly into their look at the actual language features.
Right, the qualitative part. What linguistic details did they zoom in on?
They compared the language used in responses ChatGPT got right versus the ones it got wrong within both the low and high-performing groups. They looked at word-level stuff, technical terms, character frequency, words with multiple meanings, pronouns, symbols,
Right.
and sentence-level features too. Sentence structure, noun phrases, verb complexity, sentence length, passive voice, prepositional phrases, a whole range of things.
And what patterns popped out? Let's start with the lower level group again. What was different between the correctly scored ones, LC, and the misscored ones, LM?
Okay, for the lower level group, the ones ChatGPT scored correctly, LC, tended to be, well, simpler. Shorter responses, fewer technical terms, more straightforward sentences like subject, verb, object, simple noun and verb phrases, fewer prepositional phrases. Their example was just, there are gaps between molecules that allow for transmission. Pretty direct.
Simple, clear, easy for the AI to parse, even if maybe incomplete scientifically. And the ones that got wrong in that lower group, LM.
Those tended to be longer. They often used technical terms, but sometimes inaccurately. Sentence structures were more complex, multiple clauses, things like that. More complex noun and verb phrases, more prepositional phrases. The example they gave about diffusion started. The principle of diffusion is that molecules are constantly in random motion, the higher the temperature. So using science words, but maybe mixed with misconceptions and definitely more complex phrasing.
So for the lower performers, it seems like linguistic complexity could almost mask the underlying errors from the AI, or at least confuse it. What are the high performers? How did the correctly scored HC ones differ from the misscored A?
For the higher level group, the ones scored correctly, HC, were generally longer again. They used more scientific terms and, crucially, more mathematical symbols or formulas.
Ah, okay.
Syntax was complex, multiple clauses, modifiers, lots of specific noun phrases like rate of change of magnetic flux, complex verbs, more sentences overall, lots of prepositional phrases. The example about the magnet and coil was quite detailed, even mentioning an equation.
Right, packed with detail, precision, math. Looks like a strong answer. So what about the ones ChatGPT misscored in this high-level group?
These were often shorter. They used fewer math symbols or formulas, simply sentence structures, short sentences. Noun and verb phrases were less complex, fewer prepositional phrases. The example was concise. The coil will exert resistance on the magnet because of energy conservation.
So scientifically sound, maybe even elegant in its simplicity, but it lacked the detailed elaboration.
Exactly. It seems for the high performers, being too concise or linguistically simple, even if scientifically correct, might lead the AI to underestimate the understanding. It seemed to favor the more elaborate, detailed explanations in that group.
That's a really crucial finding. So summarizing this first study, ChatGPT has potential in Chinese, but accuracy isn't quite at English levels yet, likely due to these unique language features.
Right. And the link between reasoning complexity and scoring accuracy is complicated. It works differently for lower and higher performers.
And the language itself, length, complexity, vocabulary, can really sway the AI's judgment, sometimes helping, sometimes hindering.
Definitely. It also really underlines something else. The quality of the human scoring that was used to train the AI in the first place, that's absolutely critical.
Yeah, garbage in, garbage out, essentially.
Yeah.
If the human scoring wasn't consistent or accurate, the AI won't be either.
Precisely. The AI learns those patterns, biases, and all.
Okay, fascinating look at the AI side. Let's pivot now to our second set of insights, this idea of analogical modeling competence. What exactly is analogical modeling in science?
It's a really core part of scientific thinking, actually. It's about using similarities. You take something familiar, the source, like water in pipes, and use it to understand something new or abstract the target, like electricity in wires.
Okay, like that classic water analogy.
Right. It's a creative process, finding those connections. But crucially, as the Lin and Chow paper highlights, it's not just about spotting a similarity. It's a whole process. They talk about two main phases.
Who are those?
First is what they call phenomenon-related abductive premises. Let's call it phenomena ABPR.
Catchy. What does it mean?
It's basically gathering your initial thoughts about the thing you're trying to explain the target, identifying key bits, making some educated guesses or inferences about why it happens.
Sort of mapping out the problem space. And the second phase.
That's the analogical modeling processes, or AMP. This is where the analogy work really happens.
Awesome.
Lin and Chow break it down into steps, drawing on other research. Things like selecting or building an analogy, checking if it actually fits the target by comparing features, analyzing where it works and where it breaks down, using the analogy to explain things, and then thinking about how you might apply or extend that analogy.
So it's like find an analogy, test it, figure out its limits, use it, maybe even improve it.
Exactly. It's an active process of model building and refinement.
And this Lin and Chow paper tried to measure this ability in 6th graders using electricity.
Yeah.
How did they build their assessment tool?
Yeah, grade 6, they developed this analogical modeling competence, or AMC instrument. They focused on circuits, which they called matter ontology, and energy, which they called process ontology.
Matter versus process. Why that distinction?
Well, they argue these represent fundamentally different kinds of concepts. Matter is more about tangible stuff, structure like circuit parts. Process is about change, flow, action like energy transfer. And students might need different kinds of analogies for each. Finding an analogy that works across that matter-process divide can be particularly tricky.
I see. So the instrument had to account for that. How did it measure competence?
It was built around levels of sophistication, from level 0, just based on experience, up to level 4, high-level abstract thinking.
And the actual assessment.
It had two parts. The phenomenon ABPR part used multiple choice and yes-no questions to check basic understanding of electricity concepts.
Okay, the foundational knowledge.
Right. Then the AMP part used open-ended questions. These really probed the process. How did students choose analogies? How did they compare them? Did they see the limitations? How did they apply them?
Getting into their thinking.
Exactly. They also use things like concept maps during development to link electricity concepts and potential analogies, and they validated it statistically to make sure it was measuring what they intended.
Okay, so what did they find? Did the instrument work? What did they learn about the students?
Yeah, the instrument seemed valid.
Yeah.
They found a moderate link, a correlation around 0.57 between understanding electricity concepts and being good at analogical modeling. So related, but not the same thing.
Makes sense.
Interestingly, the AMP questions, the ones about the process of using analogies, were harder for these kids. The researchers suspected it might be because they hadn't really been taught how to learn using models.
Yeah, if you haven't practiced it, it's going to be tough.
Yeah.
What about their actual analogical skills? Where did they succeed or struggle?
Oh, in the basic concepts part, they did best with simple circuits, struggled most with energy concepts.
Okay.
In the modeling process phase, many students could actually identify relationships within an analogy they showed, relational mapping.
That's pretty good, like level 3.
So they could see the parallels. But
But they really struggled with applying or deploying the analogy, especially across that matter-process divide we talked about. Many were basically at level 0 there.
so they could see A is like B, but couldn't use that likeness to predict something new or explain a different aspect. Pretty much. And many students seemed aware their first analogy wasn't quite right, that it needed fixing, but they just didn't know how to fix it or find a better one.
So they hit the limits of the analogy but didn't have the tools to move beyond it.
That seems to be a key challenge. Understanding the surface similarity is one thing. Knowing how to adapt, refine, and transfer the model is much harder.
Wow. That really points to some teaching implications, doesn't it?
Absolutely. It suggests we really need to explicitly teach students how to work with analogies. Not just give them analogies, but teach the process. Choosing, mapping, finding the flaws, adapting them.
Discussing the limitations openly.
Exactly. Providing diverse examples. Maybe even, as the researchers suggest, using AI tools just to brainstorm potential starting analogies.
Interesting idea. Okay, so we've looked at AI struggling with complex language and explanations, and students struggling with the complex thinking involved in analogies. How do these two threads weave together?
Well, I think they both highlight just how complex assessing science understanding truly is. The first study shows the tech challenge AI grappling with linguistic nuance and reasoning depth, especially outside English.
Right.
The second study shows the cognitive challenge for students, the difficulty of actually doing the sophisticated thinking, like analogical modeling, that leads to deep understanding.
And could the language issues from the first study, like using complex sentences or technical terms, directly impact how well a student can even express their analogical thinking, which the second study looked at?
Oh, I definitely think so. If a student struggles to articulate complex relationships using precise language, it's going to be hard for them to explain their analogy effectively, right? To show how the source and target map where the analogy holds where it breaks.
Yeah.
Conversely, a student with strong language skills might articulate a really sophisticated analogy much more clearly. And based on the first study, that clearer, more complex explanation might be more accurately assessed by a well-trained AI.
So it's almost like the AI's difficulties in scoring might partly reflect the student's own difficulties in reasoning analogically and expressing those complex thoughts in writing.
That's a really nice way to connect them. Language and conceptual understanding are deeply tangled, and assessing either one, whether by human or machine, runs into these deep challenges.
Okay, so let's boil this down. What are the key takeaways for listeners from these two deep dives?
Okay, first, AI scoring shows promise, even in languages like Chinese, but linguistic nuances and complex reasoning are still major hurdles. Accuracy isn't perfect, especially compared to English benchmarks so far.
Got it. Second.
Second, how students write matters to the AI.
Yeah.
Length, complexity, vocabulary, these things influence scoring accuracy, and sometimes in opposite ways for students with weaker versus stronger understanding.
Right, the complexity paradox. And from the analogy study.
Third, analogical modeling is vital for science learning, but it's genuinely hard. Students need more than just seeing a similarity. They need skills in applying, testing, and adapting analogies. And finally, assessing this modeling competence requires looking beyond just factual knowledge. We need to evaluate the process of their analogical thinking.
So wrapping up, here's something to ponder as AI gets woven more into education. How do we leverage AI's assessment capabilities effectively while still making sure we nurture that deep, creative, sometimes messy scientific thinking, like analogical reasoning, especially when dealing with diverse languages and ways of thinking? And maybe, what role does explicitly teaching modeling and even awareness of language itself play in bridging that gap between human insight and machine evaluation? Definitely food for thought.
Absolutely. And if you want to go deeper, definitely check out the original papers. Lots more detail there.